Let's look at another physical example, the planar pendulum. So this is just like a clock, the pendulum that you see in a clock. Here it's hanging from a rigid body. We need to have some values that account for some of these physical parameters. So there's a length to this bar, and that length has a mass. Then there's the mass of the end. And we have two values here that we've denoted. So Tc, that's the torque, and then theta, that's the angle measured from the vertical there. So based on these values, we can use, you guessed it, Newton's law of rotational motion. So the sum of all torques is the rotational moment of inertia times the rotational motion, or rotational acceleration. So based on these values, we can go back to the laws of physics, and that gives us the ability to write that, first of all, we have the torque Tc, that's the first torque. The second torque we actually get from gravity. So the further m gets away from the vertical line there, the more gravity acts on it. So for very small angles, the action's not much. But for larger values, you get this value g pointing down, the acceleration pointing down. So we actually multiply that by how far away it is from the vertical, and we use a sinusoid to do that. So mgl times sine of theta gives us the amount of torque that we see on the bar, and then all of that has to equal to the rotational moment of inertia I, and then theta double dot, so that's the angular acceleration. So with these values, we can actually look and see, well, I is going to be equal to ml squared. This is a value that we know from dynamics, and so if somebody looked that up in a book, they told us, yep, I equals ml squared for a bar with a mass on the end. So now we set ml squared theta double dot equal to I theta double dot, and we can do a little bit of simplification. So in this way we can isolate theta double dot on exactly one side of the equal sign after we divide it through by ml squared. So this gives us one set of equations of motion. But we can get another set too, because we fairly arbitrarily decided that theta double dot deserved to be by itself exactly over there. So we can instead decide to have all values that are with respect to theta on one side of the equal sign. This is another equation of motion, and these values are equivalent when it comes time to grading on an exam, unless I say otherwise. So for example, I might say, please isolate all values of such and such, or give values with respect to theta double dot, for example. In that case, I would prefer the top over the bottom.